Saxon Advanced Mathematics, Lesson 98. Welcome. Greetings, my students. This is a great lesson for where we are at in our journey. These are some really nice, relatively sophisticated, real-life application problems of how to work logarithms. They give you a great feel for all the tricky, interesting things that logarithms can do. They're relatively complicated, but they're going to make you feel super smart. So let's dive in. There are two types of them. The first type is called a change of base. And they look like this. Oh, but before I get into that, let me just show you what it looks like, but I want to explain one thing. This is the problem. Okay, find log 5, 15. Now, remember that this is the basic form of a logarithm. This is the base. This is what we call the number, or if you want to get really fancy, it's called the anti-log. It's the opposite of the log. And this is called the log or the exponent, right? This is called the logarithmic form, but we can also rewrite this in what we call exponential form, which is to say that the base raised to the exponent equals the number, okay? This is called exponential form. This is called log form. We can go back and forth between those two forms whenever it suits our pleasure, okay? So that stands as a review. We've known this for a long time. And notice here we have the base times the exponent, or raised to the exponent equals the number. That's straightforward. Now, what causes drama in a problem like this is that we're supposed to be finding the log of a base that is not programmed into our calculators. We don't have base 5. We have base 10, which is called the common log, and we have e, which is called the natural log. And remember, the number e is like 2.71, blah-de-blah-de-blah. It's an important number. It's a special number, but it is not a 5, and that's what we need right now. So what are we going to do with this? That's what this problem is all about, is how do we change the base to make it more findable? The first step is change to exponential form. Okay, we can do that. We know how to do that. We're going to say that, first we're going to make it an equation, sorry. We're going to write y equals log 515. Okay, that was not very hard, but that sets us up into the proper form, right? Because we need to have equals. And we could have done it in the other order, right? We could do it that way. It doesn't matter either way. John does it this way. I'm going to do it this way so that it looks a little more familiar to you because we just plunk y at the end of it. Now we're going to change it to an exponential form. So what we're going to do now is we're going to say the base 5 raised to the power y, we could also call this the power, okay, equals the number, which is 15, okay? So we've turned it into an equation. Either one of these, this was step 1. And now step 2, we take this, which looks just like that, and we flip it so it's an exponential equation instead of a log equation. Okay. And at first it looks exciting because it's like, 5 raised to what power equals 15? We should be able to do that. It ends in a 5. No, it doesn't. 5 to the first power is 5. 5 to the second power is 25. So it's 1 point something, but we can't just figure it out in our heads. The third step is now we're going to take the log of both sides. Remember, we're allowed to do that. So we're going to say log 5y equals log of 15. And now what we've done is we've converted it into a common log problem, a base 10 problem, right? We could convert it into e, right? We could use e instead. And that will work out just as fine. I'm going to work it in the common log, base 10. But the process would be exactly the same. You would just use different buttons on your calculator. All right? So now what we can do is we still have a little simplifying to do. We can jump that down using the power rule. So that's simplify. So then we'll get 4 times the log of 5 equals the log of 15. I'm sorry, that's not a 4, that's a y. Okay. And then I'm going to divide away the log 5. That cancels, so we get y equals the log of 15 divided by the log of 5. You can now go into your calculator and find both of those. So you go in, 15 log equals divided by parentheses, use the parentheses for the denominator, 5 log, close parentheses, equals, and the number that you will get is 2.2646. Let me know if you have any problems with calculating that. That is the correct number. John does the very same thing, only he, instead of using the common log, he uses e. Right, so when he takes the log here, he writes the e instead of log with the invisible 10 there, and he gets the very same answer. So you can do it either way, it will be fine. All right, so that's how we can change the base of a problem to make it fit into the buttons on our calculator. That is so cool, you guys. That is so clever and interesting and manipulative in all the good ways. Manipulation can be a bad word, but when it's applied to relationships, but it is fabulous, right? These definitely are calculator problems because you want to access that table of log values that lives in your phone. Beautiful. That's the only problem we have of that example, but it is a sweet, straightforward, very practical calculation, and I love it. Okay. Now we have a couple more problems that are slightly different in nature. And these are called contrived logarithm problems. I don't like that name because contrived sounds like fake or meaningless, but that's not true. They're problems that are designed to work out a certain way so that you can practice these skills. That's all they mean, okay? So let's dive into... Oh, I skipped another one. Just a second. There is another changing base problem. Let's do it. I got all excited about those contrived problems. Find log 7 of 82. Again, no me gusta. Log 7, it's not in my calculator. So first I'm going to rewrite this as an equation. Recognizing that I could put the y on either side. I put it on the right last time, so let's try it on the left. It doesn't matter. And now we're going to rewrite this log equation as an exponential. We stop and get our bearings. This is the base, this is the exponent, and this is the number. Okay? I did something wrong here. I was just thinking, I figured it out, but it's okay. I copied the wrong answer for you because I was thinking about how I told you at this stage that we know that y is going to have to be greater than 1 but less than 2 because 5 to the first power is 5 and 5 to the second power is 25. But I told you this answer, I copied the wrong answer out of the book. It should be 1.682 0.26. This is the answer for the problem we're doing now. My bad. Okay, but I caught it, and I'm glad that I did. And remember, this is the original question we were asked. Find log 5 of 15. That is what we found right here. Okay? The reason I caught this mistake in my brain is because I did stop and do this mental checkpoint of what answer am I expecting. So I thought that y is going to be between 1 and 2. That was my mental checkpoint. And I just realized that it failed, and that sent me back because I was doing the same thing here. Let's see. We know that 7 to the first power is 7. 7 to the second power is 49. 7 to the third power, ooh, I don't know what that is. It's 49 times 7. Let's find out. 63. I wrote down the wrong number. 7 times 4 is 28. 6 more is 34. Okay, so this is 343. So we know that y is going to be greater than 2 but less than 3, right? Because 82 falls in between these two numbers. This I'm going to keep in mind and make sure that my answer falls into the right place, because that's how I caught my mistake in the last problem. Okay. So we have we wrote this first as a log equation, then we switched it to an exponential. Now we're going to take the log of both sides. Again, we could take the natural log. We could rewrite e of 7 to the y equals e82 and use those buttons on our calculator. It would be just fine. But I prefer to use the common log. It's more of the mathematician's tool. E sort of belongs to the scientists, although we're not afraid of it either. But I'm going to go ahead and use the common log. So now I'm going to take the log of both sides. Log of 7y equals the log of 82. Then I'm going to use the power rule to jump that down. Y log 7 equals log 82. And then I'm going to divide to isolate the y. So I'm going to divide away the log 7. That cancels. And now I can do this on my calculator just like I did last time. And I will get that this answer equals, I'll get y equals 2.2646. That fits right into my expectation, right? That it would be between 2 and 3. And thus, even though this says y, my original thing I'm trying to find is that, right? I set up the y as being equal to that. So now I can say the log of 782 is 2.2646. That's my final answer. And that's what I was asked to find. Yay! Okay, I'm so happy we did that because I caught the error in my other problem and I gave us another chance. Yay. Okay, so now on to these contrived, or what I would say specifically designed problems that allow us to practice certain skills. They're cool problems. All right, they look horribly scary. Solve. Log of x squared equals log of x squared. Ooh, so subtly different. I don't even know what that means, right? It seems so confusing. Well, let's start with what we know. Let's take this and jump it down. 2 log of x equals, and let's write this out. Instead of just using parentheses, let's write this out. No, I'm going to wait one more step to do this. Okay, now what I want to do is I want to swim these guys to the same side and see what I can do to factor them. Okay, so what I'm going to do is I'm going to swim this to this side, but then I'm going to flip it so that all the information's over here. But I want this to be the positive and that to be the negative. So I'm swimming that over here. So it'll be log x quantity squared minus 2 log x. And then there will be a 0 on this side. But I'm going to flip it over. So this is what I'll end up with. Right? That's positive, that's negative, 0's on the other side. Okay, beautiful. Now, just to make this super obvious, log, this is starting to look like 10g, log x quantity times log x quantity. That's what this means, right? Minus 2 log x equals 0. Okay, this helps me explain my next step, because what I want you to see is that we can factor a log x out of both of these terms. So there's the log x on the outside. When I factor this one, I'm still going to have a log x left. Here, I'm just going to have minus 2. Okay, so that's basic factoring. I pull a log x out of each of these terms. There it is. This is what's left. This one and that. And there's the minus 2. Okay? All right. This is like old school algebra 2 factoring, isn't it? Now we know, because of the zero product theorem, that if my answer is 0 and I'm multiplying two things together, that either, whoops, the log of x equals 0 or the log of x minus 2 equals 0. So let's figure those out. Okay. Let's change this to an exponential. Our base is 10, right? So 10 to the 0 power equals x, right? Because that's the exponent that you put on the base, the invisible 10, and this is the number. So we get that x equals 1, right? Because anything raised to the 0 power is 1. And here, we have to add the 2. Log of x equals 2. And now we do the same thing. We change it to an exponential. The base is 10. The exponent is 2. And that will give us the number. So x equals 100. So we have two answers for this. X equals 1. X equals 100. That's correct. Two solutions. Which makes sense because whenever we have a square, we oftentimes find ourselves with two solutions. All right. One word of caution. When you get to this stage, one could think, let me just cover that up. One could think, wait, I want to use a different piece of paper. Okay, we're right here. Why not divide both sides by log of x? Right? Can you pretend those are fractions, right? Then that would cancel, and we'd have log of x minus, and those would cancel, 2. But that would be dangerous because then, as we see, we would miss this solution, right? We'd get this one because we'd have log of x minus 2 equals 0. That would be fine. But we wouldn't have this other solution. And that's a general rule of thumb whenever we are factoring, is we don't want to divide. We would much rather factor than divide, because when we divide by logs of unknowns, or by any factor, we lose potential solutions. So we don't want to divide when we're factoring. That's a general rule. Don't divide, factor instead. The overall problem is factoring. That's what I meant by that. But we would rather pull it to the side than divide it away. I hope that makes sense. All right? So just don't divide in these problems and you'll be fine. All right, let's do another one, because that was fun, right? It's so ugly and horrifying looking, and then you do the steps and it's like, oh, that isn't terrible at all. I think we have 2 more. Let me double check. 3 more. That's all right. We're having fun. We're in no hurry, right? You don't have anything better to do with your life than watch me do log problems and try to figure them out. I know. I don't have anything better to do either. This is my best life. It's another like tongue twistery, right? The log of the square root of x equals the square root of the log of x. Oh, good Lord. All right, the first thing that we would like to do is get these pig houses out of here. As cute as they are, they do not help us. So we carefully rewrite this to the 1/2 only relates to the x. So we can write like that. This one we have to relate, oh, sorry. the 1/2 to the whole thing, right? Because the whole thing is in the pig house. Okay, so if we've switched to fractional roots, that's much better. Now we can jump this fraction down, right? 1/2 times the log of x equals, okay? So there we have that. Now, what we want to do is square both sides to get rid of this, right? So what did we do here? We changed to fractional exponents. That's what we did first. Then we used the power rule to jump this down, right? And now what we want to do is square both sides. And the reason we want to do that is it'll get rid of that, right? So what we're doing is we're multiplying by the reciprocal, right? So that when we multiply by 2/1, those will cancel to become a 1 and they can go away. But then we have to do the same thing. We have to square this side, right? So what we'll end up with here, this side will be cute, but this side is going to be a hot mess. We raise the 1/2 and we get a 1/4. And now look what we've done to that side. The left side got crazier, the right side got simpler. All right, that's fine. Now, we're going to try factoring this again, okay? Let's bring this over to this side. So we'll have, so we're going to rearrange and then factor. So we're rearranging with factoring in mind. So we're going to bring this over. So we'll keep this 1/4 log of x squared. We like this one first. It doesn't really matter, actually. That's the minus equals 0. Now I'm going to rewrite this just to clarify that there are 2 of them there. Wait, I wrote this wrong. Sorry. That should be that, right? Because we got rid of the exponent. So I'm just making that up. Okay, now we see that we can factor out log of x. So we'll rewrite it. Here's the factored out log of x. We're left with 1/4 times the log of the other x minus 1 equals 0. Because there we factored that all out. So we just have to placehold with a 1. All right. Hopefully you survived that factoring process. Now we're ready for zero. Some people call it the zero factor theorem. Some people call it the zero product theorem. But the idea is that if the product is 0, then one or the other factors have to be 0. So that tells us that either the log of x equals 0 or 1/4 log of x minus 1 equals 0. Okay? So now we can rewrite this to an exponential. We could say 10 to the 0 power equals x, and anything to the 0 power is 1. So there's one of our solutions. And now we have to fix this one. We better add the 1. And then we better multiply both sides by 4 to get rid of this fraction. Log of x equals 4. Okay, now we're ready to go exponential. 10 to the 4th power equals x. So that is x equals a 1 with 4 zeros. 1, 2, 3, 4, and that's 10,000. Yay! These are the right answers. All right. Why would we be doing problems like this? That's a good question. Last time we were motivated because we had problems that were written in logs of bases that we don't have on our calculator, so we were rewriting it so we could solve it in a handier way. Why would we even have problems that look like this? Don't worry about it. There is no rational explanation for that. What we're doing here is just practicing our ability to manipulate. And it's fun, right? Okay, we're on 5. We have 2 more to go. And these are faster, I think. They look faster. 98.5. Solve. Okay, this is a bit of a brain twister. 10 is the base, 3 is the exponent. The number that we get is log x. That doesn't look like a normal exponential equation to us, does it? But if we just keep calm, we can keep figuring it out, right? This means, again, the invisible 10 there is our base. This is our number. And this is our exponent or power or log. All of those words apply. So I rewrite, right? Base to the exponent or power equals the number. But now we have another one. I'm going to write it in the other way. And I'm going to expand this number. It's a 10 with 3 zeros. So now we can rewrite it again as an exponential. This was like a log in a log. This whole weird thing, right? Now we can do it again. The base is 10. The exponent is 1,000. Whoa. And the number is x. What the heck? Crazy, right? We don't have to write this out. It would be 10 with 1,000 zeros after it, and that is the right answer. Okay? This one was hard because this original expression did not look like a normal log. But if we just stay calm and remember our basics, we can rewrite it as an exponential. But when we write it, we realize, it's still a log equation. It had a log buried inside a log. And so then we did it a second exponential. And that got us where we needed to be. Yay. Right? That's this one. My arrow doesn't look very good. Okay, so then we did it again. Okay. 98.6. Last one, solve. Oh, brace yourself for this. This is crazy. Have you ever seen anything as disgusting as that? It's hideous. But even though we have a little log written up here, this is considered exponential form. So, and if you will notice in these problems, we tend to be going back and forth from log to exponential to log to exponential. That's a strategy we use to break these problems open. So we can see that even though there's a log up here, this is basically an exponential equation. So we're going to take the log of both sides. So I'm going to take the log of x raised to the log of x power equals the log of 10 to the 8th. Okay? Now I'm going to use the power rule to jump these down. So the first thing I did was I took the log of both sides. And then the second thing I'm doing is I'm using the power rule to pop those exponents down. So we will have square root of the log of x times the log of x equals 8 times the log of 10. All right. That's not horrible, right? Now, this we can simplify because the log of 10 is one thing that we can always remember. The log of 10 equals 1, right? Because it's the base and the exponent. What's the exponent that we put on the base of 10 to get 10 is 1. So this becomes 1. The log of 10 equals 1. That is always true. So this becomes 8, right? Then the other thing that I'm going to change in this one, also in this third step, is I'm going to switch to fractional exponents. Okay, so this log of 10 is 1. 1 times 8 is 8. So I've simplified the right side. This part of the left side stays the same, but I'm going to change this to the 1/2, right? We don't need pig houses in our logarithms. We generally always want those out. Now I'm multiplying matching bases. And remember, our rules for exponents say that if we're multiplying matching bases, we can add the exponents. This one doesn't have an exponent. I can give it one. I can give it a 1. But I need to add it to this one. So what would be more helpful would be to give it the exponent of 2 over 2. That's an exponent. It's not floating very well. So I can write log of x 3 over 2, where I've added those, equals 8. That means that before I switch this into an exponential, I want to get rid of this. So what I can do is multiply both sides by the reciprocal of this exponent. Then when I multiply, this becomes 1, and I just have log of x. So my fourth step is eliminate the fractional exponent. With the reciprocal, right? Okay, so that's why I use the 2/3, because that will neutralize that. I have to do it over here. I can find 8 to the 2/3. We find the cube root of 8, that's 2, and we square it. Right? I multiply by 2, I raise it to the power of 2/3 to neutralize this exponent. This becomes 1 and it goes away. I just have a log of x. I also have to raise this to the 2/3. 8 to the 2/3 I can calculate. First I find the cube root, that's 2, then I square it, and that's 4. What the heck? And now look, now I just have a simple little log equation that I can solve as an exponential. And it is 10, that's the base, to the exponent 4 equals x, or x equals a 1 with 4 zeros. 10,000. Crazy roller coaster rides, right? Of doing kooky things to try to make, I mean, basically what you can do, you guys, is try to make the most obnoxious thing go away. This is the most obnoxious thing. We want to be able to jump it down. In order to do that, we have to take logs of both sides, because you can't just jump it down on a regular number. But if it's the log, yeah, you can, right? We jump it down, then we convert it to a fractional exponent, because who needs a pig house in the middle of their log equation? Not me. Get rid of the pig house. It's disgusting. We switch it to fractionals, we combine, and then we eliminate, and it all just falls into place. Hallelujah. These are not easy problems. I do not even pretend that, but they, I think, are oddly satisfying. And do you not feel smart? You should feel like a genius. All right? They give us review in some of sort of the moderate basics, like we remember our rules for exponents and we remember our fractional rules. But you guys, this is a great example of a problem that proves why we need to review for the AccuPlacer in a very different way. There are so many simpler ideas lying way under the surface of a problem like this that you've forgotten all about. Simple little calculations, and we need to go back and refresh those because this is very advanced mathematics, and the test is going to test you on your basic to intermediate skills. So, love this, enjoy it, make the most of it, but just realize that this is why we need the review, because this isn't going to be on the AccuPlacer. Much, much easier tests will be. So, I'm crossing out number 98. Look, we only have 2 more lessons. Oh, so exciting. Okay, that's all I have to say. Thank you. Goodbye.